probably are here. I think there were a few people that were here for the first time, which is great. Love it. Wonderful to have you. The Peninsula Astronomical Society has been around for
1940s.
1940s, yeah.
Crazy.
So a long time. A lot of really avid amateur and professional astronomers. And a very diverse group. And a very passionate individual and people who are beginners and very advanced as well. So it's a great way to learn from each other. Membership is only $25 a year, which also highly gorgeous if you aren't already a member. And we have many benefits, including a loaner telescope program, which allows you to check out a telescope, try one out for the first time ever, or try something new. So we also have a facility in the mountains, the Santa Cruz Mountains, where we have an observatory, and we host public programs every Friday evening from 9 to 11 at the Foothill Observatory on the Foothill campus, and also solar observing Saturday mornings, 10 to noon, and so it's also really interesting. So you're welcome to come to any of those anytime. And he does one of our telescope operators, telescope operators. So that's something else that many folks get to do as members. Without further ado, I'm going to turn it over to Antonio, who's going to tell us about our speakers.
Yeah, and I see all sorts of age ranges. One of our club members was enticed because we told her that if you join the club, we'll teach you how to operate the telescope. Consider that, and if you're younger than 18 years of business. But I really recommend you take this Professor Mathews. So with that, I first of all want to thank again Dr. Mathews for agreeing to deliver his talk on a very interesting subject. I don't know how many of you have heard of OUMUAMAU. Show of hands. Okay. This is visitors from out of this solar system. A lot of really crazy theories were going at the time. Some of them may or may not be disproven, but other ones we're hoping that Dr. Mathews here will shed some light on what really happened, what was going on. I'm not going to describe too much because you would raise their hands. And there's something happened. Something came to our solar system very quickly. So anyway, we're very excited to have Dr. Mathews here talking what happened and what may or may not happen. So thank you very much for that. Thank you.
Well, thank you, Maria. Thank you, Antonio, for having me come out and speak this evening. Glad to see all of y'all here. Also, I appreciate the sales pitch for the classes. So yes, I'm Geoff Mathews, and I'm the full-time astronomy professor at Foothill College, and where we do have a couple of different lecture courses we offer, and along with a lab class. And I've got count four students here, five students out here. So sorry, it's too late for bonus points this quarter. But yeah, so I will be speaking about something that I don't really give much time to in my courses, right? Because you have this class, you have only so much time, right? In astronomy, it turns out is kind of a really big topic. It's kind of the study of everything. And so for any course, having to be very, what am I going to fit in? What am I not going to fit in? And so one of my favorite topics that I kind of always end up having almost on the cutting room floor is OUMUAMAU, which was our first discovered object from outside of our solar system passing through our solar system. And so because of that, right, because of those origins, I was a little tempted to have this as the title for my talk instead. I was a little tempting, but I realized that my Photoshop skills were really just not up to the task of doing this proper the credit that it's due. So instead, just going with something a little bit more straightforward. Now, I will also be talking about Oumuamua from the perspective of a professional astronomer who's not a specialist in this field, right? Because this has been fascinating to watch as it has gone, as we've gone through time, as you know, sort of the initial measurements, the initial discovery has shown up to the public, as then, you know, sort of further measurements were being made, as people started bouncing around ideas to explain what we saw with this object. And so a lot of my talk is going to be from kind of almost a very personal perspective of, like, as an outsider for this corner of astronomy, what has this process looked like? And so when I say as an outsider from this corner of astronomy, meaning, you know, I'm trained as a researcher. I did a PhD in astronomy at the University of Hawaii, where I specialized in using radio interferometers to take baby pictures of solar systems. So this is actually kind of one of the neighboring corners of astronomy, where I was studying the places where objects like Oumuamua are being made. And so, you know, so I did this work with radio telescopes, taking pictures of, and I just realized this laser pointer is probably not going to show up on that screen at all. Okay, so, you know, so where, you know, we would be able to actually take pictures of the material around young stars, where things were being formed and where they could then get kicked out from, as ends up being the case with Oumuamua. So, spoiler alert for the next 3 slides. You know, and I did studies of the gas content of disks, which is also a topic that's going to show up in our view of Oumuamua. But also, so that's kind of my research background. You know, so that's the science knowledge and skill set that I'm bringing to the table to try to understand what's going on in this neighboring corner of the field. But also, you know, my focus over the past decade has really been on astronomy education, where I've had to be a generalist. And so I've had to put a lot of my time and mental effort into learning more about all of those other corners of astronomy. When you get a PhD, you learn everything about almost nothing. And so, and so it turns out that there's a whole lot to astronomy beyond the circumstellar disks of material where planet formation occurs. It turns out that there's a lot of other topics. And so my focus on education has given me this time to delve deeper across a greater breadth of topics. And so that has also provided me some tools to bring to bear on this topic. Now, I've been talking around, what is this topic? What is this thing that we're talking about? So Oumuamua is the first object that humans discovered that as it's passing through our solar system, that came from another solar system. The name itself is meant to convey that. So loosely translated, Oumuamua comes out meaning scout, right? It's this first to you know, be ahead of others from afar. And this image here is the actual image in which it was first noticed. So this comes from the Pan-STARRS telescope on Maui. This is a telescope that it's a robotic telescope that's designed to search the sky for things that are moving, designed to search the sky for things that are changing. Now, a lot of that focus has been motivated by the search for the asteroids in our own solar system that can potentially someday hit us, right? That's been one of the major drivers for Pan-STARRS, is the search for near-Earth objects. which means if you're looking for things that are most likely to be in the future a danger to us, you're actually looking at a kind of a limited slice of the sky. So Pan-STARRS does do some searching of the whole sky, but it really focuses on this narrow slice of the solar system along the plane of the planets where the asteroids are found as well. And so that little tiny streak that's shown up, that showed up in that image, and I forgot I added this in. This is one of the things I was doing while giving a final exam today, was going through and adding in like, oh yes, and I should throw in some photographs of Pan-STARRS telescope. And then of course, forgetting that I'm doing a photograph of it, right? So, this is showing the dome of Pan-STARRS on Maui. But this object identified on October 19th, 2017, set off a flurry of activity in the astronomical community. Someday I would love to do just interviews of all the people involved in this to find out, how were you able to get time on 8-meter telescopes in less than 24 hours? I suppose it's probably easy when you're calling somebody up and saying, hi, we've got something from outside the solar system. So that's my guess, it's an easy sell. Whoever had that night on the telescope was like, I could keep working on my science here, or I could help get some data on this once in a many lifetimes opportunity. And so very quickly, basically every research telescope on the planet that could point off in the right spot on the sky was trying to observe this thing as it was flying through our solar system. And so this is what you end up getting once you have figured out how it's moving, and you can have your telescope tracking the object itself, as opposed to just taking a long exposure image of a patch of sky. So Pan-STARRS is scanning the sky, looks off over here, I forget how long the exposures are, but take a long exposure, and anything that's moving shows up as a streak. You then have software that identifies, oh, there's a streak that's shown up here. And in the case of this streak identification with Pan-STARRS, right, a lot of work has gone into automating, interpreting those streaks, figuring out what we're seeing, because it's way too much data. I forget the exact number. It's terabytes a night, maybe not terabytes, but a huge amount of data every single night. Way too much for a person to look through all of the images. And the vast majority of what it spots is just another asteroid. Oh, another dozen asteroids. Right? That's what typically happens during a night, is, oh, just another, massive pile of asteroids added to the collection. But things that are unusual get flagged. And so then in the morning, or even during the night, maybe the system emails folks to be like, hey, take a look at this. Let's have a human take a look at this. And so it's a nice example of sort of how automation can actually be helpful to us, as opposed to just a scary thing, right? It's taking care of the routine. Yes, yet another asteroid. Let's let the humans focus on the new interesting thing. And so this gets spotted by Rob Varick in the morning. And so again, sort of hitting the little personal note side of this, I happen to know Rob. He was my neighbor when I was living in Hawaii. And so it's like, oh, that's so cool. There's definitely a cool element from, sort of seeing these names showing up on papers. And I'm just like, oh yeah, we used to do beach barbecues together, sort of thing. But so very quickly, Karen Meach and others kind of organized this big effort to try to use every resource available to observe this object. And observe they do, for as long as they could. I checked the Minor Planet Center and found 240 some odd entries of observations that were carried out of OUMUAMAU over the span of just 2 months. 2 months, basically, 2.5. So spanning from when it was first identified on October 19th, 2017, on into November. By November, basically only the largest telescopes were sensitive enough to be able to keep observing it, right? But this thing was moving so quickly, it was moving away from Earth, plus Earth moving in its orbit, that it was receding from view and getting fainter and fainter and fainter from our perspective. So that very soon, so within a month, only the largest telescopes could observe it. And by the final observations, January 2nd, 2018, by the final observations, it took, let's take the Hubble Space Telescope and have it just stare off in this patch of sky for who knows how long. I forgot to look up how long those observations were. Now, this also prompted people to say, hey, let's take a look at other images collected around this time. Maybe somebody else saw it too, but just didn't notice it. And it turned out that that was actually the case. So it was spotted in an observation as early as October 14th with the Catalina Sky Survey. And so this is all we got. And this is an object that's moving away from us so quickly, we can't do more. We can't get more data. And this is kind of fundamentally the heart of the story of OUMUAMAU. Incredibly interesting object about which we can really only know very, very little. Let's go over what we do know. We know the path that it followed. So we tracked its motion from, so here I have a video showing its motion from discovery October 19th. It was here and Earth was here, so it was just past Earth. And then continuing on its outward trajectory, and of course, Earth continuing on its orbit. So these two things combining together to make it harder to see this thing. It's moving incredibly fast. That's how we knew it was from outside of our solar system. Within the solar system, the sun's gravity can only make things move so fast. And so when this thing was spotted moving at 26 kilometers per second, that was clearly from outside of our solar system, because nothing inside our solar system can go that quickly. And so its path was observed. Measurements were made to see how well is it reflecting sunlight in many different wavelengths. And so this is overall what we refer to as color. So this is one of the first reports of how it has reflected light down in blue-green, in red light, and then in several different wavelengths of near-infrared, along with a comparison to types of objects that we found within our own solar system, right? Because this is how we start trying to make sense of things. What did we see? What are other things we've seen? Does this look like other things we've seen? And in many wavelengths, the slope of this, people are looking at this saying, hey, this looks pretty similar to several different types of things that we've seen in our own solar system. It looks similar to, say, this pink line, which is D-type asteroids. Oh, it looks similar to this dotted line, which is Comet 67P. So, okay, it's looking similar to some things that we've seen in our own solar system. That's going to be helpful for trying to make sense of it. We start with what we know. We have measurements, and so then, of course, people are thinking, well, hey, what are types of things that we see in our own solar system that are zipping around like this, little tiny things that are zipping around? Well, we see asteroids and we see comets. Well, how do we really tell those two things apart? How do we tell apart asteroids and comets? Well, the real distinguishing feature of comets is the whole fuzzy thing that they have going on, right? Comets famously look fuzzy when we look at them. If they're really releasing a lot of material, they might have a tail of material being left behind as they're passing through the solar system. So like here are a pair of images I took of comet C2017K2. They have such poetic names, don't they? There's so many of them, right? You can't give them all a name anymore. But where we see, the stars are looking like points, not as point-like as they should. I was getting these images just from my local park, but so not the best observing conditions. But then the comet clearly has this cloud of stuff around it. And so people said, well, hey, let's try to see, can we tell, does this look like an asteroid? Does it look like a comet? And so taking a look at these images, you can say, well, let's start at the center here, work our way to the side, just plotting out how much light are we measuring. And at the very center, nice and bright, we move a little bit to the edge, it looks dimmer, a little further to the edge, looks dimmer, further to the edge, looks dimmer, and it just drops off sharply. So it did not look like it had a cloud of material around it. So a lot of the early thoughts were, oh, is this an asteroid? Or maybe a really depleted comet, a comet that has already tossed out everything it's going to toss out. And there's a question mark. There were also noticed, and this is where things started to kind of feel a little weird, really big changes in brightness over about 7 or 8 hours, where there's basically about a factor of 10 change in brightness from the brightest that this thing appeared to the dimmest it appeared. Now, we only had really measurements that were good enough to really measure this for not very long, just a few weeks. Because of course, as things get further away, as they get fainter, it becomes harder to make a precise measurement. But we could tell immediately, wow, this is some really big changes in brightness. In fact, we had not seen anything in our own solar system that changed brightness by such an extreme degree, a factor of 10. Well, what is that telling us, right? It's telling us that it's rotating that it's extended in shape. And when the long face is towards us, we're getting a lot of light reflecting off of it towards us. When the end is facing towards us, like at the beginning of the video here, when just the little end is pointing towards us, there's just not a lot of surface area there for reflecting light our way. And so there was some later work that was really looking into kind of the nitpicky differences in brightness at different times to work out that it actually wasn't the shape that was initially thought, right? The initial thought was, oh, it's this very long cigar-like shape. But because sort of the pattern didn't repeat nicely, you can kind of see where people took data from multiple cycles and were kind of overlaying them in different ways. They were able to piece together that it's actually shaped more like a pancake, a very puffy pancake. So maybe like a poffertje, if you had those in the Netherlands. So very kind of puffy pancake. So kind of a 1-to-5 ratio in terms of the diameter versus the thickness on this thing. And not spinning just one way, it's kind of wobbling. So a very complicated motion for this object. So, okay, some really extreme changes in brightness, suggesting kind of an extended shape. Yes, yeah, so this is a visualization. And I'll explain. So the last work I found really kind of looking into the motion of this in detail, so the fact that it's the last thing I was able to find tells me, okay, kind of everybody's been like, okay, it's solved, right? When you have a continuing series of papers, it's like, oh, people who are the experts in this area are still not happy with the answer. When you're like, this is the last one, it's like, okay, I think that they've decided that this is as close as we're going to get to the answer. And so it's this nice paper from 2019, where the author also produced a visualization of it. Now, we don't know details like how craggly is the surface. So that was kind of added in for artistic measure. Really, what we know is it's a big roundish thing, about 5 times wider than it is thick. And then the further details are just artistic. So then things get a little weird. So people are observing this, that measuring its position as precisely as we possibly can, given the constraints, given the constraints of the size, 100 meters. When we're talking about comets in our own solar system, we're finding things that are a kilometer, 4 kilometers, 10 kilometers in size. So this is smaller than any comet that we found in our solar system. We found asteroids that are of this type of size. But as far as comets go, this is smaller than what we found. Well, so then as we go to the end of 2017, we're like, okay, we're just about out of time to be observing this thing. It's looking very asteroid-like. It's not active. We're not seeing any dust flying off of it. Spectroscopy has not shown any measurements of gases coming off of it. So people are like, okay, it's this very asteroid-like object. It has kind of a weird extended, a shape that is more extended than we might expect. But okay, this gives us something to chew on, something to think about for a while. But then so the extended measurements of its motion. See, this is the problem with making edits while I have students taking a final exam. So I then end up forgetting my order in which I have things. So then we end up seeing that its trajectory is not quite what we expect. We're thinking this is an inert lump of something, and it's on its path, and we've got the sun's gravity pulling back on it as it's moving, but instead, there's an extra little component to its motion. About 0.1% of the sun's gravity outward push. Oh, it looks like there's some folks at the door. So this 0.1% of the sun's gravity outward push, that's knocking it very slightly off the expected path. So by the time of the last observation, it's off of the predicted path by about the size of the Earth, which doesn't sound like very much when you're saying, oh, this thing is now twice the sun's distance away from us, right? So this is at a time when it's more than 2 astronomical units away from Earth. It's moving, I said it's moving fast, right? This thing is moving at a very fast clip. And its position is off by 1 Earth. Now, it doesn't sound like much, but it's a significant measurement. And it was surprising. And for something to have this additional component to its motion means that there's got to be something happening to give it an extra bit of push. And that's when we start going into now we've got a serious mystery phase. So up to this point, we had a nice set of measurements. Okay, nice little set of things that we've measured. These are all the things that we can definitely say. We know, where its closest path was by the sun, approximately. Because of course, if it's been outgassing, then when we try to work the trajectory backwards, that's increasing our uncertainty there. But for the times that we are observing it, we have a good sense of overall how well it was reflecting light. We've got an overall sense of its rotation period. We have these measurements of gas coming off of it, which actually were non-measurements. We did not detect anything. We did not detect any water coming off of it. We did not detect any CO coming off of it. But we're able to say, well, if there had been this much or more, we would have detected it. So we know that the amount was less than this. So if there was any, it was less than this. So we have upper limits on these gas measurements. So not to dwell on the big table filled with numbers. Okay. And so, it showed up on, TV shows. There was a bit on Seth Meyers with OUMUAMAU as a guest on the show. I didn't find it, I don't know, didn't hit my humor, but maybe some people enjoyed that one, right? It showed up in the New York Times a little bit, a nice intro article. And then we have this mystery with its trajectory. And that's when things really kicked into high gear with OUMUAMAU. And this is where it really started becoming interesting to me as an outsider to this field, watching what's happening. So when this acceleration was noticed, right? We had ideas for all of these other things about it. The motion of it, it was moving at a speed very close to the local average speed of stars. So we're like, okay, it's from a nearby star. Maybe it's launched out from a nearby star forming region. Okay, sounds reasonable. It has this stretched shape. Well, we got some ideas for how that can end up happening. Just erosion over time. Think about a bar of soap, right? How, as you use a bar of soap, it goes down into this thinner and thinner piece. Okay, that can apply as well to something traveling through space and getting, bumping into things, right? Being eroded as it's traveling through space. Or maybe the event that launched it from its solar system caused it to kind of break up and go into an extended shape. The fact that we didn't see any material blowing off of the surface, well, maybe it's just already blown off everything that it can blow off, right? So maybe it's been around for long enough that it has depleted its surface. The same could go with the gas. Maybe it's just been around for so long that it's lost everything that it's going to lose. But then this acceleration, wait a minute, it's got to be losing something. There has to be something being the jet to give it this extra push. Now, some people jump to interesting possibilities, right? So the most interesting of all possibilities could be that, it's an alien spacecraft. But when this gets suggested, I look at that and I'm like, that is both the most interesting and the least interesting possibility. It's the most interesting because, yes, please, I want to meet aliens, right? That would make me happy for so many reasons. That would make me very happy. But it's least interesting to me because where do you go from there? It doesn't lead to anything testable. It doesn't lead to many testable ideas because aliens can do whatever they want, right? If somebody has the wherewithal to make something and send it flying at our solar system, then yes, they absolutely can make it gas tight with nothing leaking. They absolutely can make it so that no dust is going to be chipping off of the surface to give it a coma. Oh, they can make it whatever shape they want so that, whatever your light curve is, you can make a spacecraft that gives you that light curve. The fact that the motion is close to the local average, we can come up with 20 reasons for an alien spacecraft to be moving close to the local average from, well, it launched from a nearby star to, oh, they're intentionally disguising the origin of the spacecraft. Even the acceleration of this thing, it could be, they've got jet thrusters that are releasing material at a rate too low for us to discover, or it could be a solar sail and light pressure is giving it an extra push. We've seen this with objects in our own solar system. So for that reason, I'm like, looking at that suggestion, I'm like, that's just not very interesting. And I'll be the first to say that at the end of the day, for OUMUAMAU specifically, we'll never know. We have 2.5 months of observations, period. We're not getting more. Not without some just incredible superhuman effort to send a spacecraft out, right? So barring that, we're not getting more information about it. But what we can do is we can explore possibilities. And that's been, for me, that has been my favorite part of this, has been watching the process of people sitting down and doing the what if thinking. What are possible things? Possible, taking into account what we know about solar system formation, taking into account what we know about the types of things that form in solar systems and how things can get tossed out of solar systems. What are all the possible things that this could be? Because that is then giving us a to-do list of things to watch for in the future. So those possibilities, I got to admit, the way that I have encountered these possibilities as people have come up with them has been by reading the news. And then I've said, let me go, somebody's put out a new paper. Let me go track that down, right? And so I've been finding out about these things at the same pace that everybody else has, right? So, June 27th, right? Like I heard about OUMUAMAU, I talked with some of my friends back in Hawaii about it. And then I didn't think about it again. I was like, well, that was cool, but we're done learning more about it. And then this acceleration was discovered, and that then led to conjecture, these ideas. Hey, maybe it's releasing some gas, and so it is cometary, and it was just releasing so little material we couldn't detect it. Then an idea that maybe in the environments in which stars form, you get these regions that are just really dense and incredibly cold. And you could conceivably make something cold enough that the hydrogen itself starts freezing out, making a hydrogen iceberg. That's a really interesting idea, and that builds on some interesting physics. And I was like, wow, that's kind of an interesting corner case, and that gives us a thing that we can look for in the future, right? Because I can immediately hear that and start saying, aha, what observations would I make to check for that? Okay. And some of those might be difficult observations. Like the first thing that comes to mind is like, well, H2, it's kind of hard to detect actually, but I know that, if you happen to spot it as it's near the sun, the ultraviolet can be triggering these emission lines from the H, difficult, but I can imagine experiments to actually test it. Other ideas coming along with, an idea of, hey, maybe it's not a hydrogen iceberg, maybe it's a nitrogen iceberg. So something like Pluto that's very nitrogen rich. If it had some catastrophic collision, could have torn off a piece, gone traveling through the universe. And again, I can think of observations that I could make to actually check this idea, right? It would be looking at a different set of wavelengths than what people were able to observe for as OUMUAMAU went by. Look at the date here, 2023, 6 years later, people are still actively thinking about this, trying to come up with what are possible things that could explain this. And it was those first cases, hydrogen iceberg, wow, we haven't seen anything like that. A nitrogen iceberg, yeah, we haven't seen anything like that in our own solar system. But we can imagine it based on the fact that we got, Pluto and the other Kuiper belt objects that are very nitrogen rich. Like, okay, we can imagine some kind of collision knocking material off. And then finally we get, somebody has finally had enough time to think through a way that, oh, how could just a regular comet end up looking like this? And so this article is referring to a bit of work led by I forget her first name, Bergner up at Berkeley, if I'm remembering correctly off the top of my head. I should have taken better notes as I prepped. But so a bit of work led by a chemist actually, right? And this has been the great things watching this, is it's not just astronomers getting in on this game, right? This was such a discovery, right? It drew the attention of people from other fields entirely to bring their expertise to bear, to say, oh, what happens if you have a big chunk of water, CO2, CO with some dust mixed in, And you have that traveling through interstellar space for a long period of time, getting exposed to that cosmic ray environment. Oh, that's going to cause this water ice to get broken apart, but leaving little cavities where the H2 that gets produced can be trapped, and actually crunching through the math to say, okay, what if? What are the scenarios under which this could produce enough hydrogen that could then get released to push your remaining object for that little extra bit of acceleration? And there's a nice bit of work where there's more of a feasibility study. Because remember, we're never going to know for OUMUAMAU. We're not going to know because we're not getting any more data. But what we can do is we can evaluate feasibility. We can say, here's a scenario, taking a type of object that we just see left, right, and center, right? All over the place. We see comets, chunks of ice, water ice, CO ice, CO2 ice. And somebody's crunched through the math to say, what would happen to one of these things moving through interstellar space for millions of years? Okay, you're going to have cosmic rays. That's going to be your big interaction. And crunching through the math, crunching through the physical chemistry, the chemistry calculations, what's going to be happening to those materials in that comet. To say, oh, you're going to end up with a layer, a meter thick, 2 meters thick, 3 meters thick. Lots of uncertainty there. We're not quite sure. So we don't know the answer on that. Okay, let's just do the calculation for all those possibilities. How much light, how well is this thing going to heat up as it passes near the sun? Again, we don't really know. It's just a huge question mark. Okay, let's just do the math for a big range of possibilities. And when they did this math for this big range of possibilities, they found that, yeah, a lot of these possibilities lead to this thing having the acceleration, being able to have the acceleration that we saw. So it's feasible. And that's the best that we're going to be able to say in the case of OUMUAMAU. But more importantly, it gives us ideas for observations to make when we start spotting more of these things. So just helpfully kind of listing out these potential natural explanations that people have considered. Now, all of these ideas that people have proposed, there's problems. There's problems with all of them. Okay. And so the thing is, it's those problems that lead to people then sitting down and doing the hard work to come up with the answers. To say, oh, well, yeah, the nitrogen iceberg problem, the nitrogen iceberg idea, man, for that to be plausible would mean that there'd have to be a whole lot more Plutos out there than we think are out there. Okay, so we can probably toss that one. Even the hydrogen pockets, some people have been like, well, there are some other effects when you have this hydrogen leaving that might lead to a cooling. That might be a challenge for this idea. But all of these lead to things that we can look for as we start spotting more of these. And spotting more of them, we will. Realizing in my usual fashion, I've prepared way too many slides. So already the second interstellar object has been spotted. So I2 Borisov, or 2I Borisov, and it ended up looking basically like the comets we see in our own solar system. It wasn't, and it was discovered by a lone person, working at their telescope, which is amazing. And that's the way that for the longest time comets were discovered. Now most comets are being discovered by these automated systems. And so I'm like, all right, humanity, one last win for humanity here. But what that's really telling us is that these objects that are making it to our solar system from other solar systems, they're going to have a big range of properties. That makes sense. There's a lot of other places out there that they could be coming from. The travel times, there's going to be a huge variety in travel times. Some of them will have been lucky enough to have just done a straight shot from someplace nearby. Some of them might have been moving around in the galaxy for many millions of years, for incredibly long stretches of time. And so I'd like to finish with just a real quick back of the envelope calculation. So I thought I would include the envelope where I first started thinking this through. Now, how many of these things should we expect? So when I started exploring this question, I was so pleased to find that in March of 2017, so March, wait, so that's 7 months before OUMUAMAU was discovered. There was a paper where, reading this paper, I get to the end, and in the conclusion, they're like, we're kind of getting worried now that we've actually really misunderstood some fundamentals about solar system formation, because we've had pan-stars running for a while now, and we should have seen something from outside of our solar system by now. What's gone wrong? Where did we mess up? That's my paraphrase of how this paper reads. So this was expected. People were keeping an eye out for an interstellar object, and for good reason. Just doing the back of the envelope calculation, OUMUAMAU was spotted when it was 1/5 of an astronomical unit away from Earth, and then by the time it was 1.3 AU away, it was just too faint. And so there's basically approximately a 1 cubic astronomical unit region where we can spot these things. Spot things like OUMUAMAU. Okay, again, this is very rough back of the envelope calculation. Okay, so we can't spot them looking towards the sun because we got the sun over there. It's just too bright, blocks our view. Okay, so looking away from the sun, there's kind of a spot over here where we have a chance of spotting these things. Well, so then, and OUMUAMAU crossed that in a month. So but within a month, it was so far away that something like pan-stars has 0 chance of spotting it. Your survey telescopes cannot spot it. Once it gets that far away, it's too faint. So, because all of our studies after that were with big glass, were with these 8-meter, these 10-meter telescopes, or with Hubble. So we have a limited time to spot them, a really limited region. Well, so now we can ask ourselves, just how many of these things should be out there? Well, our galaxy's got about 250 billion stars. And those 250 billion stars pretty much all would have gone through the planet formation process like our own solar system. As the stars formed, there would have been a big cloud of material around them, and that out of that material, asteroids and comets would have formed. Now, we saw in our own solar system, a lot of those objects got tossed out of the inner solar system and out into the Oort cloud, where they're just this big spherical cloud and occasionally get nudged to fall in. And those are the comets we end up seeing. The estimates are that there's something on the order of 1 trillion comets that are 1 kilometer or larger in the Oort cloud. So there's going to be even more of the small things like OUMUAMAU, right, 100 meters. Now, this process of tossing things out is a messy one. And so something like 10 to 100 got tossed out of the solar system entirely, right? So for every comet in our solar system is shared 10 or 100 with the rest of the galaxy. So what happened here, it's safe to assume, has happened everywhere. So we've got 250 billion stars, each tossing something like 10 to 100 trillion comets out to share with the rest of the galaxy. That's 1 trillion, just in our back of the envelope estimation here. But it turns out that space is very big. And so our galaxy is like 100,000 light years across, 1,000 light years thick. And so that comes out to about 10 to the 27th cubic AU. So remember that cubic AU is our little detection region, our little space where we actually stand a chance of spotting one of these things. Well, so then we can just look at the ratio of those things, right? 10 to the 24th of these interstellar objects. Let's just back of the envelope calculation. They're just spread out evenly. That means that at any given time, there's the density of these things is about 0.001 per cubic AU. And thanks to how fractions work, we can just treat that as kind of odds, right? There's about a 0.1% chance that any particular cubic AU has one of these interstellar objects at any particular time. So once it's there, how long does it stay there for us to be able to detect it? Well, that's about 1 month. And so this telescope that made the discovery in the first place, NANSTARS, it had really been operating at its full capacity, right? It took some time, right? I remember when I first went out to Hawaii in 06, it's like, okay, it wasn't there yet. But within a few years, it was actually up and really running. And so it had been going for about 100 months. And so you just multiply these numbers together, and it's just like, just from our quick back of the envelope, we're like, okay, 10% chance that we would find one of these things during this time period. Now, this is just my quick back of the envelope, right? If you go through and you really nitpick the details, and there are some places where we're like, well, we don't know. Is this number 1? Is this number 100? Right? When you go and you take into account that variety in all these numbers that can go into the calculation, you get things running from 1% to 100%. And the people who wrote that paper, right, their conclusion was, we're thinking 100% here. Why haven't we seen anything yet, though? Right? That's why they were worried. Because they're like, we were really expecting to see something by now, and they hadn't. And so, and some people, the places where we didn't know the answers yet, they're like, well, it's only a 1% chance by now anyway, so don't worry about it. Okay, so there's this range in the estimates, but just kind of the quick estimate here gets us to 10%, which is just not a crazy number, right? It's like, okay, it's not surprising that we spotted something. And if we had missed that one, we would have had Borisov a couple years later. Though it was discovered by a human. So, which is great. So my point here is that it would not be surprising for an ice ball launched out from a forming solar system to be passing through our solar system at the time that it was spotted passing through our solar system. And then when we combine this on the other end with a theory that is feasible from physics that we know of the composition of these things, what happens when you send an ice ball through interstellar space for a long time, can that get you to a condition where you can then get something that's just non-detectable in terms of the emissions? So one of the slides I zipped past earlier that I prepared was basically kind of, if we take into account the small size of OUMUAMAU, the fact that we didn't, actually, no, this is really worth making this point. So I know I'm like really pushing up on my hour here, but this is a really, okay. So when we scale, so just I just picked one of the numbers out. Okay, because I was able to quickly find a comparison among comets known in our own solar system, right? So people made these measurements of gases coming off of comets in our own solar system. So I found a very nice survey from a couple of years ago looking at dozens of comets. And so I've kind of trimmed down the table just to emphasize a few. All these comets are different sizes. So if you want to be able to compare them easily to each other, you should scale by their size. And it needs to be their surface area, not just their diameter, right? Because where's that gas coming from? It's coming from the surface area. If you have more surface area, that's more places where gas can leave your comet. You have less surface area, that's just fewer places for gas to leave your comet. So if you are comparing by taking into account this surface area, it makes for an equal comparison. So when we do that, this really low limit to what we detected from OUMUAMAU scales up to a much larger number. When we scale, if we imagine scaling OUMUAMAU up to the size of the typical comets that we've studied in our solar system. So this this non-detection of about 10 to the 24th, CO is coming off at less than 10 to the 24th molecules per second. If it was the size of a comet, of the other comets in our solar system, if it's a kilometer, that would be less than 10 to the 26th. Well, now if we can start comparing to the comets that we've studied in our own solar system, for example, Inky. That scaled number for Inky, we have detected it emitting at a rate of 0.025 times 10 to the 26th molecules of CO per square kilometer per second. The limit that we have on OUMUAMAU, it's just not meaningful. It's like saying, I've tried to measure Geoff's height. He's less than 10 feet tall. Is that actually a helpful, is that a helpful limit on my height? And there's a huge variety among the comets that we've studied in our solar system. We're looking at that last column there, right? 0.013, 7, right? So some are just emitting huge amounts of CO off their surface. Some are just barely, losing track of where I am in my slides here. Some just barely emitting any. And so we see a huge variety in the properties of the comets in our own solar system. We have a lower limit, or we have a limit on the emission from this thing passed through our solar system. That's not even a meaningful one. If you made observations of a comet in our own solar system and you said, well, maybe it's releasing some CO, but it's at less than 10 to the 26th molecules per square kilometer. The people who study comets in our solar system would be looking at you like, yeah, go get another night on the telescope, buddy. You need some greater sensitivity for your measurements. And with OUMUAMAU, we don't have that luxury. But with the next interstellar visitors, we will, because we're getting some serious upgrades. So Pan-STARRS, 1.8 meter telescope. Soon, Rubin is going to be online, 6.3. So more than 3 times greater diameter, which means almost a factor of 10 greater collecting area. That greater collecting area gives you greater sensitivity. That means you can be spotting things further out. That means that you can be spotting smaller things even, right? Which already I'm like, wow, this thing was 100 meters across. And just the thought of finding things that are 50 meters across as they're passing through is exciting, right? So these upgrades that humanity is about to get, I'm really looking forward to. And the people who've crunched through the math in detail on this, said, well, this is extending the distance where we'll be able to detect things. That's extending the time that we'll be able to detect things. And so that combination of factors, we're expecting multiple of these per year, possibly. So exciting times ahead. And as we build up numbers, we will then have context to try to go back and make sense of OUMUAMAU and Borisov. It's only when you've got tens of these, dozens of these, that you can then start to say something like, okay, was this truly unusual, or is it just one of many? And that's a story that we've been through many times. Asteroids, first discovered in the 1850s. Kuiper belt objects, finally kind of acknowledged as a separate class of things in the 90s. We've been through this before. We see this with things like fast radio bursts. First, there's only one weird thing, but then we start finding more and more. And it's when we have the more and more that we can actually start to say something. And I think that, speaking of saying things, that's kind of the end of what I have ready to say. Thanks for having me. And I'm glad to take questions. So I don't know, do y'all normally moderate questions or just leave that up to me?
Yeah, go ahead, but I want to make sure eventually that if there's anybody online.
Oh,
Yeah.
got it. Yeah, yeah. So people give you.
Start the process and we'll work it out.
Okay, I saw your hand go up first and then Kata and then.
These objects incorporate in the galaxy, or
Well, yeah, so this is all part of our galaxy, right? And so they are on a path through our galaxy. They've been tossed out of wherever they formed. OUMUAMAU, it turns out, its motion was very close to sort of what we refer to as the local standard of rest. And so where we look at the nearest, I forget, 1,000 stars or something like that, and average up their motions, it was moving very close to that average, which is suggesting either that it's come from one of the local star forming regions where basically the gas is kind of moving it close to the average. And so then when it forms stars, they're moving close to the average. And so then anything that gets kicked out from those stars is going to be good. So there's kind of a chain of reasoning there. Or that it's been drifting for so long and just kind of having random interactions that whatever its original motion was has kind of gotten averaged out over time. But yes, it is also moving, orbiting around in the galaxy. So within our solar system, right, from our perspective in our solar system, yeah, it's moving in at some very different path. And so it looks like it has just fallen in like so, come close to the sun, been yoinked around to come off in this other direction. And so it looks very close to a straight line, but it's not quite a straight line. And with our precision measurements of position, we could actually tell, what is the shape of that orbit. Now, those videos I showed earlier showed sort of the working backwards to figure out the trajectory. Those are under the assumption of, well, nothing extra going on, only gravity. If this thing had some big outgassing event as it was coming into the solar system, it could have been on a quite different path, as it was coming by the sun. So big unknowns there, big question marks as to its prior motion. And so when people try having these kind of detailed discussions about the origin location of OUMUAMAU, there is that big, question mark. We don't know what it was doing before we spotted it. Okay, so I'll get her question and then yours, okay?
So recently, or not recently, I'm not sure how far back it goes, the project, but there was a mission called OSIRIS-REx that probed an asteroid and brought back a sample. I was wondering if we had that sort of technology or that same thing back when OUMUAMAU was coming around, would that have changed things?
Okay, so would having so we've been doing these spacecraft visits to asteroids and comets for a long time. Like there was a spacecraft, I think there was a spacecraft fly through with Haley ages ago, if I'm remembering correctly. But we've had missions. I have no idea what the number is. It's in the dozens of spacecraft visiting objects within our solar system. The thing is, even within our own solar system, it's a challenge to sort of, move further out from the sun, right? You're having to, and some of the ways that we do that was just with really big rockets, right? Sometimes we handle this using things like gravitational assists. So doing fancy maneuvers where we fly by a planet and get a little gravitational boost from it to get our spacecraft further out to go visit these other objects. OUMUAMAU was traveling way faster than the fastest things that we've ever launched. And so I don't know off the top of my head what it would take to, I know people have done the calculation though, because there is discussion of even now potentially putting together a mission, but the effort for it, like the rockets that you have to line up for it. And then of course, to get something moving faster, it's a lot easier if it's lighter. And so, less mass. And so that means, okay, you're having to make your spacecraft even smaller so that you can give it enough lift to get it moving fast enough to potentially catch up. Now, one of the ideas going forward is the idea of having kind of our own little scouts, right, in place. So you can have spacecraft kind of prepare, orbiting around at large distances, already with large rockets. So you can do fancy things like, oh, let's spend 10 years putting this together by getting our spacecraft out there, then launching more spacecraft with fuel to all kinds of fancy ideas for how to do this. And so it all comes down to effort effectively. And so it's not the case that we could have diverted one of our probes that's already out there, right? We couldn't have just told something, oh, pull the handbrake, right? We could not have redirected anything that's out there to go visit it. But in the future, we could potentially have things ready to go. But again, that is a decades-long effort, right? That's the sort of thing that somebody could say dedicate a career in aerospace to accomplishing. Not to drop any hints as to, suggestions for students in the room, but, all right, question.
I just want to point out in your presentation, you kind of look at the sun and its solar wind as a very even, smooth thing. The sun is an incredibly crazy thing.
Oh, yeah.
It almost looks like it's going to blow apart sometime. And so a map of what really, the path that it actually takes to there is much more complicated.
Oh, absolutely. Yeah. I sort of mentioned, that it could have had outgassing events, but absolutely, right? The sun's effect is variable. And so, yeah, big question marks.
On a personal note, on November 10th, 1960, I stood underneath a rippling curtain of light in Chicago. The solar storms had moved the northern lights down, and I've never seen anything like that. I lived in Denmark and was in Norway. I've never seen anything like that. But somehow the solar storms did that, and it was incredible. Yeah.
Oh, yeah, those interactions of the solar wind and the Earth's magnetic field.
I was also at the University of Iowa kid. And I was a physics student back in when that early stuff was being done.
Oh, such an exciting time.
Oh, yeah, and I can actually, they have a really good website. I can go back and find papers that I saw personally back then. But we live in this amazing solar system. I mean, this area here. This is a very good presentation, though. I thought let's point that out how crazy this one was.
Oh, thanks. Yeah, and that's absolutely, one of the things we have to acknowledge when we try to backtrack OUMUAMAU's motion is that there's a lot of stuff that could have been influencing that we never saw, right? Because our first data is from October 14th, when it was already past the sun, already passing Earth. So, wait, real quick, I wanted to do a quick check. Were there any questions coming in on Zoom?
No, okay, let me unmute myself. It might be a little bit of an echo. Of those people that are still in the Zoom, feel free to send a chat or raise your hand and we'll take notice. Thank you.
All right, so go ahead and get your question while you watch the chat.
I think you said the speed was 26 kilometers a second, which is extremely fast.
Yeah.
What is the normal speed?
Yeah, so the cutoff where we identify something at these distances, the cutoff, if I remember correctly, was like 21 or 22 kilometers per second. And that's basically what is the free fall speed. Imagine some object out at infinity and you just, so effectively an Oort cloud comet and you nudge it straight towards the sun. How fast will it be moving when it's at 2 AU or 1.5, whatever the distance was that it was detected? And so you crunch through that math, and it's something like 20 kilometers per second. There have been, comets that have been right at that line, where people have said, well, maybe this is an interstellar object. This is the thing that was so far past the line, right? That we're like, nope, this is absolutely clearly from outside of our solar system. The things that are right on the line, we've gone with Occam's razor, right? We said, well, this is the safest bet is that this is some Oort cloud comet that has been nudged in and it's on its very first pass into the solar system. So, and I don't know much about those 5 or 6 comets. As I was preparing this, part of the fun of preparing a talk like this, by the way, is like, I get to learn more about these other fields. And most of what I learn is like, how much more I have to learn. And so I was just like, ooh, that's an interesting tidbit. I should go read up on that again later when I have some more time to go read about, because one paper mentioned, oh, and there are these 5 that, were right at the line. And so that's all I can say about them is that they have been spotted, but this is the thing that was clearly over the line. All right, a few more questions?
Yeah, I'm kind of curious as to what the greatest magnitude was. That was detected coming in.
Oh, so when its detection magnitude was 19.5, so incredibly faint. So to give people a sense of perspective in the magnitude system, this is a way of talking about brightness where 1 is like the brightest things, 2 is dimmer than that, 3, 4. And every 5 magnitudes is a factor of 100 in brightness. The faintest things that the human eye can see is about magnitude 6. Or if you're talking about me, about 4. And so on a good night. And so so when it was spotted, so 19 versus 6, so 5 gets you to 11, another 5 gets you to 16. So 100, so that's 10,000. And then you're like another 3 magnitudes past that. So that's like another, factor of 10 or 15. So something like 100,000 times fainter than what the human eye could see. And that's when it was spotted. You remember that Discovery image? That's just super faint little streak on the image. Amazing. So, I think about the software that was written to detect these moving objects. Actually, it's called Moving Object Processing System, MOPS. And astronomers, we love our acronyms, right? And it just mops them up. But I think about the work that went into this and how sophisticated that code has to be. And I think, man, I'm so glad it's not me having to do it. It's a lot of work. And yeah, I code, but I'm not good at it. Other questions?
Well, this is probably a dumb question, but you
That's
said the trajectory was off from what was expected.
Yeah.
And then you started talking about acceleration.
Yeah, so the calculation is done where we say, okay, we're not seeing any activity from this thing. So let's do all of our math, just assuming that it is an inert lump. Okay, so in that case, the only thing operating on it is the sun's gravity. Oh, and you got Jupiter over there. Okay, that's an extra little tiny modification. Earth just doesn't count. It's just not,
Or just a little bit.
Well, and so, yeah, that I'm not sure, right? I'm not sure to what degree that was being included. So they said, okay, from just the pure gravitational calculation of motion, here's what the path should have been. But it ended up over here. And from the observations, it looked like it was a pretty steady thing, but it was dropping off with distance from the sun. So the further from the sun it got, the weaker the effect was. And I think that people settled on it being like a 1/r² thing. So, which a lot of stuff in the universe goes is, your distance squared. And so then that prompted people to think, well, what are things that change in strength that way? And so one of these ideas is, just light itself pushing against it. So this light sail idea, right? Or we've seen other objects that are not light sails get pushed around by light itself too, right? So not necessarily a light sail, but so this light pressure drops off as 1/r squared, okay? But there are other things that can too. Even the activity of a comet can drop off as it's getting further away and cooling down. And so basically when we see something that's not where it should have been, we can calculate kind of what additional acceleration would have needed to be going on to get it over here instead of here. And when that, sort of working that backwards, that turned out to be an acceleration about 0.1% of what the sun was causing. So an extra little tiny push. And that's a really solid observational result. Like we know that it had this little extra push at this rate of 0.1% of the sun's pull. And it's when you have a thing happening and not enough data to really pin it down, that opens you up for all kinds of fun conjecture. And sometimes not fun conjecture. So, yes.
Maybe it'd be a naive question, but given the fact that there's so many objects in the Oort cloud, and all this hypothesis about the age, what happens with comets over a very long period of time, by conjecture, you would think that there may be very ancient comets that we should be able to detect in the plane of the, our expected plane of the solar system.
Well, so the comets that we see today are, so we have to backtrack. How is it that we end up seeing a comet today? So the comets that we see today are on these very kind of extended orbits. Okay, that's how we figured out that there's this reservoir of them really far out there in the first place, because they had to come from somewhere really far away. How could these things have gotten really far away? And they're in all directions, right? They're not just in the plane of the solar system. Everything else, the planets, the asteroids, the Kuiper Belt objects, they're all in this same plane, which tells us that they all formed from the same material, right? That was, my goodness, that was Speedenberg in 1734, figured that one out. And later Immanuel Kant got credit for it. So I may be being a little unfair, but only a little. So the comets, though, they're coming in from all directions, right? We see them coming from there, but it's coming from there, from there. And so that's telling us that they're arranged in a big spherical arrangement, okay? And then from kind of the statistics of the ones on these really extended orbits, the ones on short orbits, they've all like had a close pass by Jupiter or Saturn that's kind of adjusted them into a shorter orbit. But from the statistics of these really long period comets, we've been able to figure out roughly what the distance is, working backwards, kind of estimates to the numbers. I don't know the details of all those calculations. It's another one on my to-do list to read through the work by Oort. Got the paper downloaded. But we can't see them. They're out in the deep freeze. They're too small. We don't spot them until they've fallen in and come in past Jupiter's orbit and start evaporating. That's the only time that we can actually see and study them. So everything about them further out, we were inferring from what we see of the ones that drift in close. So I'm not sure if did that answer your question? Did that address your question? Yeah.
Okay.
Yeah. So,
We'll cut it to one more question and then we'll close it.
all right. Yes.
How would be automated detection? Just look at this thing going very fast from point A to point B, it's be faster than the other features.
So the way it works is, wow, I did put way too many slides. So pan-stars, it's these survey telescopes, right? So it's not just pan-stars. There's several of these going now. The way that they operate is they're scanning the same patch on the sky over and over and over. So not just once, not even one time per night. So for some regions of the sky, they're going back half an hour or an hour later because you want to see where something has changed. And so they're taking the image. They've looked at this spot on the sky dozens of times already. And so they've made an average of that. They've made a median of that. So they're like, this is what this patch of sky normally looks like. And so then they're looking for something that has changed. And this ends up telling us not just about things that are moving, right? So during the, I forget how long, 30 seconds or whatever, right? OUMUAMAU moved from here to here, right? So made that little super faint streak. Right, so it's looking for streaks like this. That's how we spot something that's moving quickly in our solar system. It's also able to identify things that are changing in brightness. So these automated systems, they've just given us an overwhelming number of novas and supernovas and anything where something is changing in brightness. It's actually, yes, overwhelming is what I would say about sort of the number, just the sheer number of things being found by these. And so to your question about how does it know that this thing is moving? Really, the streak is what gives it away. Yeah, and so they'll do something. I wish I should have thrown in an example because I found a very nice example showing where they take, here's the new image from the night. Here's what we know this patch of sky looks like. And you just subtract. And most everything just disappears, right? But the thing that has changed is still there in the image. It's such a clever technique, this difference imaging. All that's left in the picture is the thing that's changed.
Thank you.
So I'm sure you can stay a few more minutes after this, it's going to close out the session. But, and I have a request for you. For the next one that comes out of the solar system, we'd like to have you back.
Oh. So I'll counter with, let's wait until we got like 10, because then we can actually start to say something other than, wow.
Thank you very much.